Remember that this is the last talk of the program.
Yes, indeed.
You will end the program.
Right.
No pressure.
No pressure, indeed. So welcome everyone to the last session of the conference. So I've been told that I can self-chair. Feel free to ask questions. I mean, this is I'm going to talk about some ideas that are actually quite old by now. So it's mostly based on this work that I did with Cheryl Shook. So it came out already 5 years ago. And so I think the thing that I'm going to talk about, the majority, they could have been done a long time ago, but somehow life got in the way and they didn't. But so I just want to encourage this discussion, tell you what the issues are, the difficulties, and whether there's hope for progress or not with these techniques. So my talk is about extremal flows for the non-positive bootstrap. Well, okay, to begin with, I cannot change slides. Okay. Okay, so as we've seen in the conference, so the unitary bootstrap has been enormously successful. So we've seen that there's all these small islands that you can get for various theories. And really the crucial ingredient is that you have positivity. When you have positivity, this implies bounds. And crucially, and this is really what we care about, it's not so much the bounds themselves, is that the bounds, they are often saturated by interesting theories. Okay, so it's interesting. So in this case, so this is the canonical example. So this is a bound for 3D CFTs, and there's some big allowed region here. But really, the most exciting thing about this plot is that we can find something that we know living here on the edge. Otherwise, when this is just some boring curve, I'm not sure. It's nice to have bounds, but maybe it's not so exciting. What's exciting here is that it's this statement that interesting theories will tend to saturate bounds. And so we can ask, why should this be the case? So let me give you a very simple heuristic argument. The argument goes like this, is that in these theories, you have positivity. So positivity, they're just linear inequalities, usually on OPE coefficients, which allows you to say that some CFT correlator is essentially a sum of positive things. And now what you're going to do is that you're going to explore in the space of these correlators, and you're going to try to optimize some quantity, like you're going to maximize some gap or maximize some OPE coefficient or whatever. But of course, you are always subject to these constraints. So the reason why bounds exist, of course, it's because there are these constraints. And so to get optimal results, you will saturate as many of these constraints as possible. Initially, all these OPE coefficients, they might be positive, but then as you try to optimize, many of these quantities will go down to zero until at some point you cannot push any of these coefficients further to zero. And at this point, you reach optimality. So the statement is that extremal CFTs then, or CFTs which will tend to saturate bounds, they are sparse. So they are sparse in the sense that there will be many OPE coefficients appearing in the correlator, which will go to zero. And since typically we are what we call an interesting CFT, usually it's a CFT which has lots of nice properties and symmetries and so on. These will also tend to be sparse. And so perhaps this is a justification for why what we call interesting CFTs tend to saturate bounds. And so in this talk, basically, the idea is that we'll try to use sparseness instead of positivity or unitarity as our starting point to try to bootstrap theories. So of course, an important remark is that I say that extremal CFTs are sparse. So almost none of these words are well defined. I mean, so extremal, I'm not telling you exactly what it is. Sparse, also, what does it mean? Sparse, for instance, the 3D Ising, the spin field correlator, we believe that at high energy, it's chaotic. It's going to have an exponential degeneracy of states. So in which sense is this sparse? I think it's sparse in the sense that there are very efficient approximations to the Ising correlator, where this ensemble of many, many states, this chaotic spectrum, is well approximated by containing just a few. Okay, so at least at low energy, the spectrum should be sparse. In the UV, it's well approximated by just having a few states. So again, I'm going to use sparseness as our starting point. And you should think that if you have sparseness and positivity, then you get the bounds. But we'll actually just try to focus on this part here. So let me recap the idea of the bootstrap, so and how you get constraints from crossing. So we have some collection of CFT correlators. So the labels I, J, K, L are labels on the external operators. You can choose some set that you like, some finite set. And then we know that when you use the OP on these correlators, you get expressions in terms of the OP coefficients. And crossing symmetry becomes a set of equations which are just some quadratic forms in these OP coefficients. So schematically, given some collection of correlators, you get a set of equations that look like this. So they are quadratic in the OP coefficients. There will be several crossing equations labeled by this index A, depending on the ensemble of correlators that you choose. And then using the OPE, each operator will contribute some kinematic object, this what I call F. So the important thing about this F is that it's a function of cross ratios, which is purely kinematic. So you know how to compute it exactly. And then you have the dynamical data, which are these OPE coefficients. Okay, so you are interested in solving these equations. And so this is just some quadratic equations for these lambdas. So to make this manifest, we can write this equation in a slightly different way. We're going to take these OP coefficients that depend on the external states, and we're going to package them into some vector, okay? Such that now these equations, they look like some contractions of these OP vectors against some matrices. Each matrix, so for each value of this index A, you have a different matrix. And then, of course, the constraints also depend on the cross ratio. So you get, but the important thing is that these are quadratic constraints on the lambdas. And so I've put into this vector all the couplings to the external states. Okay. So now something that's very simple that we can do is just introduce polar coordinates for the vector of OPE coefficients. Okay, so we're going to write this equation in terms of the norm of the OPE coefficient. So now this is a number and some orientation inside this external state space. Okay, and we're going to think of this orientation in that space as a new set of quantum numbers for my operator. Okay, so now each operator depends not only on the usual quantum numbers, so scaling dimension, spin quantum number, some global symmetry charge, and so on, but will also associate to each operator some orientation in this external state space. I mean, this is not usually how things are formulated in the bootstrap, but so my key point is just to point out that if you do this, then you get linear equations on the norm of these OPE coefficients, okay? At the cost of introducing extra continuous quantum numbers. So and this is in fact, so it's linear in these squares of OPE coefficients. So this is just the statement that usually we want to think of these bootstrap constraints in terms of semi-definite programs, which involve positivity of matrices, but we can always do this trick, introduce some auxiliary vectors to make it just an ordinary semi-infinite linear program. And so this will kind of be important for what I have to say next. But this is, of course, equivalent to the way that you heard the bootstrap described in the first week. Okay, so now what do we do to make progress? Usually what we must do is that instead of working with the full set of crossing constraints, we have to truncate to discretize. And to do this, we will pick a basis of linear functionals, some finite basis, what I call these omegas. For instance, these omegas, they could just be some derivatives with respect to the cross ratio evaluated at a point. What's important is that it's a finite, and hence these crossing vectors, now they become just some ordinary vectors. They are not functions. They're just finite dimensional vectors. That will depend on the quantum numbers, of course. But for any choice of quantum number, you just get some vector. And so the crossing equation now is just some linear equation involving a continuously infinite set of finite dimensional vectors. So let's try to exemplify now a bit. So let's consider the simplest possible bootstrap equation, which is actually what happens if you just look at a single correlation function in a 1D CFT. So in this case, this formal equation just looks like this. So the only quantum number that you have in this case is just the scaling dimension. This crossing vector is just some function that it's known explicitly. And so I'm going to do this trick. I'm going to truncate, introduce some bases of functionals. They could be just derivatives if you want. And so the equations that I'm interested in is the sum over the states in this correlator is equal to some target. So this T I call the target. It's usually just the identity, but if you want, you can add extra stuff. For instance, if you want to bootstrap some correlator where you know that there is some operator with some OP coefficient, then you can just put it explicitly into these dot dot dots. Okay, so now this is a linear system of involving n equations. And so the reason why the bootstrap, if you don't have, so you have a linear system of n equations. The way that the bootstrap works is that even though this in principle, it could be solved trivially by just choosing a random set of n vectors, the bootstrap does not allow you to do this because you want these coefficients to be positive. But now we are throwing away this because we want to consider non-unitary setup. So how can we still get some non-trivial constraints? So the idea is to use this sparseness, and this is really, I think, here the idea goes back to Gliozzi, and this is essentially the idea of his method, is that if you restrict the number of vectors that you allow in your solution, then you'll get constraints. Okay? So in the simplest case, for instance, if you have n equations, let us try to solve these equations using n over 2 operators. Why n over 2? Because there are n variables overall. There are n over 2 OP coefficients and n over 2 scaling dimensions that you have to choose. So overall, there are n variables, there are n equations, and so you might hope to find a unique solution, or none at all, actually. There might be no solution with real parameters, but in any case, this is a much more constrained problem. And so I say n over 2, but of course, if you have extra information about the system, then you can relax this somewhat. You can include more operators. What's important is that you want this counting of degrees of freedom to match. You have n equations, so in principle, you would like to have n degrees of freedom. So we saw in Marco's talk that actually often this is not what people do. You have more degrees of freedom than you have equations. And so then you have some landscape of solutions, and you have to come up with some criterion for choosing the correct one. So in this talk, I will advocate that you should, well, I will propose that you don't do this. I'll propose that you should always aim to have the same number of degrees of freedom as the number of equations, so as to hope to have a unique solution. This will partially succeed, but not quite.
Miguel, why can't you said sometimes you won't have an equation, but these F deltas, they typically will be linearly independent. So unless in some very degenerate choices of dimensions or so, are there some non-trivial cases when you don't have a solution for n over 2?
there's always a solution, but the parameters, they might be complex,
Which parameters?
like the deltas.
Why complex? If I pick n over 2 deltas, then typically these f's are going to be linearly independent. So I should be able to find real lambda squareds. Maybe not positive, but
Yeah, I mean, many times it works, but sometimes it will not work.
I think it's just miscounting. There's n variables in n over 2.
There are n variables and n equations.
N equations and n over 2 vectors. So it's not just linear independence that gives us.
That's what I was saying. Yeah, but there's also the OP coefficients. I mean, so it's a system of n equations for n variables. I mean,
I think I understand what Benoit said. Yeah, sorry, I think it. Yeah, I think I understood what Benoit said.
Okay, like experimentally, sometimes I find that it's not possible to find a solution, at least with real parameters. Okay, so this is the idea of sparseness, and so as I said, in principle, you can find a unique solution or a discrete set of solutions. You don't expect to get manifolds of solutions in this case. But the positivity of these parameters is not at all guaranteed. So usually you would think maybe this is a bug, but actually here it can be a feature, right? Because this is what we are trying to do. We are trying to get solutions that do not have positivity. Okay, so how do you solve these equations? So usually, as we saw in Marco's talk, so actually he gave also 2 or 3 ways to solve this, but I wrote this before his talk. But basically the idea is that you use what is called the method of determinants, which is simply the fact that this equation means that t is linearly dependent on these vectors. And this is not a trivial statement because these vectors, they do not span a basis. And so this will give you constraints. And you can formulate these constraints by putting all these vectors into a matrix. And you see that there are more rows than there are columns, and yet it has to be a degenerate matrix, and so there has to be some minors that vanish. Okay, but for me this is really not the most efficient way to do it. Very far from it, because these minors, they are not all independent, and of course a trivial way to get these minors to vanish is just to take 2 identical vectors, then all the minors will vanish, and you learn nothing. So a better way, in my view, is to formulate the problem as follows. So we rewrite our equation by introducing some auxiliary vectors. We're going to introduce n over 2 of them. These auxiliary vectors, they can be whatever you want, but they should be linearly independent amongst themselves and from the other guys. So a very convenient choice, you'll see in a minute, is to choose these vectors to be derivatives with respect to the scaling dimension of the other guys. Okay? It might seem a bit unusual, but we'll understand why in a moment. But in any case, so if you do this, now if you put all these vectors into a matrix, you have an n by n matrix. You can invert it to solve this equation. Okay? So it's just the inverse matrix dotted into the target. And so you learn that the rows of this matrix, which I call alpha n's and beta n's, basically they tell you everything that you want to know. So the coefficients mu, they will be the action of these rows that I call beta, which are the duals to the derivatives. You want them to kill the target. And the OP coefficients, they will be computed by the action of these rows, which I call alphas. So how should I think about these alphas and betas? Well, they are really a basis of the dual space. So you have a linear vector space spanned by these n vectors and their derivatives, okay? And these are functionals. These are covectors that act on that space. And this gives you a perfectly good basis for that dual space, which is different from the basis of derivatives. It's a rearrangement of the set of derivatives or whatever elementary functionals that you began by choosing. And so Gliozzi is this, the constraints that you have a sparse solution is really these equations here. So the statement that all these mu i's, all these auxiliary vectors, they have to decouple. They cannot be present in the solution. This is equivalent in the sense of the method of determinants because, of course, you know, this is an inverse matrix, and you compute the inverse matrices by computing some determinant and minors. So, of course, in the end, it's all equivalent. But I think maybe this is a bit clearer. So questions about this? Okay. Okay, so I told you how to solve this problem. And so what happens if you just play in this simple bootstrap case with trying to find these sparse solutions? Well, as it turns out, in this case, it always works. In this very simple bootstrap setup, you can actually find these solutions for all n. Okay, so Gliozzi's method in this case just works beautifully. You can even take n to be 100, 150, whatever. It will work, and it will construct a solution for you. And the solution might come out to be non-unitary. The way that you solve these equations, again, the equations I'm talking about, it's these beta equations here, right? These are simply some non-linear equations in these deltas. Okay? Because these are known functions. How do you solve them? Basically, you have to make a good enough guess for the parameters, and then you can use Newton's methods on these equations to find a solution. Okay? And if you have better functional bases, this will be easier to do. I'll comment on this later. But the message is that you can do it. Furthermore, for fixed n, you can start with one of these extremal solutions, and you can continuously deform it by solving these equations, again, using Newton's methods. And this I call extremal flow. So for instance, if you take the external dimension of the correlator that you're bootstrapping, you can vary it continuously, and you can find a line of solutions, all of which are sparse. So let me show you how this works. So here's an explicit construction of the spectrum of the extremal solution in the simple bootstrap problem as a function of n. And I forget if it's the number of derivatives or the number of operators, but in any case, it's very large. I mean, in all the examples that Marco spoke about in his talk, n was like, I don't know, 10, something like this. So in this very simple bootstrap problem, you can push it very far. You can see that quantities are converging. So for instance, this is the dimension of the leading operator. It's converging to some finite value. The dashed line is because in this case, we know what it's supposed to converge to. So yeah, as you add n, you introduce new operators into your extremal solution, and there's always n over 2 of them. And I should emphasize that actually this very simple bootstrap setup, even though we didn't do it in our paper, it's equivalent to the bootstrap setup in the modular bootstrap without spin. And so much later, there was a paper by Hartman and friends basically doing this technique for that case, and they also push it to very, very large n, much larger than this, maybe 1,000 or something. But it's exactly the same method and the same procedure.
Miguel, can we discuss this a bit more? So you are solving one-dimensional bootstrap, right? So when there is just one variable delta.
Yes.
And you are showing us this class of that you can construct this large class of solutions, which you call extremal solutions, via this method where you first add derivatives and then you solve these equations beta t equals 0. And in your case, we see also that these solutions, they seem to converge to something nice as you increase n, or actually they do converge. So, okay, so what is the general lesson from here? I mean, is there some general lesson that we should draw, or that?
Well, so let me
because for Marco, nothing was convergent, so that was a big problem with what he was doing. So are you saying that if he did things your way, then maybe I'm jumping ahead? Feel free to tell me that I should just wait.
Well, I think it's just the problems that he considered, they are harder than this one. Because in this one, there are no discrete quantum numbers. There's only delta. Once you have discrete quantum numbers to play with, it will become harder. So this is just the ideal case. Yeah, we'll see what goes wrong next.
But for example, in your case also, okay, so you found this class of extremal solutions in this one-dimensional problem. But do you think that there are more extremal solutions like this in one dimension, or because you found just one, which is presumably just GFF, or some other case?
Yeah, in our paper, we found other ones. Yeah, there are many other ones that you can construct in this way.
Even in 1D?
In 1D, yes. Like
Okay.
OP maximization for some random operator, it will be exactly the same logic.
Okay.
And in fact, once you have one extremal solution, then you can deform it in a gazillion different ways. So you could start off with this solution for GFF with n equals 150. And now you can switch on some other operator continuously. And you can just solve these equations iteratively to find functionals and solutions associated to this new deformation. So you can explore along many possible directions.
Okay, thanks. It's getting more clear.
So one example then is.
I mean, how do you have to read the plot? So I fix n and then I see the spectrum.
So sorry. So for fixed n, these lines, they tell you the dimensions of the operators that appear in the solution.
Okay, and the lines to the right are just guide for the eye, no?
Sorry?
The lines to the right are just guide to the eye.
These are just guides to the eye, yes.
Okay, thanks.
So this is just to intend, the reason why we're able to do this so well, it's because you see that it's easy to predict as you vary n, where the operators will appear. So I told you that you have to use Newton's method plus a guess. So this is how you guess it. We did this plot and say, I know. If I increase n by 10, I will get 5 new operators, but I can guess where they will appear. So you just make a good enough guess, and then you use Newton's method to really go to the exact solution.
Okay.
But, yeah, for each n, you just cut this plot, and you get the vectors that appear in this solution.
Can I ask also another question on this?
Yes.
I guess it's related to what Slava was asking. So, and I also asked it a little bit offline, but now I think it's better to ask it now. So is there an expectation or so as far as I understand this, there are extremal solutions here. You are guaranteed that there is one because you have at least one region in which you have positivity. So there should be an extremal solution for the problem, say, of gap maximization. Is there a guarantee or an expectation that in a generic case, you will have an extremal solution to start with to use a seed to start increasing n?
So there are two things. I mean, first of all, here when I've described these very special solutions that have n over 2 operators. In more general setups, this will just fail, even with unitarity. So this will not work. But to answer your question, yeah, I'm not sure. I don't think it's guaranteed. In general, if you it might be that you'll find a solution, but the scaling dimensions will be complex. Some of them will be complex. So it's possible that there are no solutions. But it's usually hard to verify, as you know, right? Because you have to probe this multidimensional space. So how do you know that you really found all the minima? It's hard to say. But sometimes I can see that if I start off with a solution and I start flowing it along one direction, at some point the solution seems to disappear. I cannot flow further. So I interpret this as some scaling dimensions becoming complex or something.
Okay, thanks.
So okay, I've constructed these.
Can I ask a question about the previous slide? So why are some lines bold versus some lines being just
Why are some lines what?
The curved lines which represent the spectrum?
Why did I color some and not the other ones?
Yeah.
If I had colored all of them, this would just be a big rainbow, and it would be impossible to.
Okay.
It's just there's no reason. It's just to look nicer.
Okay.
So what are these extremal solutions that I found? As it turns out, these are the solutions which saturate the bound on the gap in one dimension. Okay, so you construct these solutions, and then you can just check that these are precisely the solutions. So there is a bound similar to that 3D Ising plot that I showed at the beginning of the talk. For 1D CFTs, you can do the same plot. It's a lot more boring. It's just this half here. There's an extremal solution saturating the bound. That solution, so which you can construct by doing the numerical bootstraps, SDPB, whatever. If you do that, you will find precisely the solutions that I've constructed in a different way. I will explain why in a second. But so my point is that once you have one of these extremal solutions, as I said, you can just flow. You can flow by varying delta phi continuously. And in particular, you can make delta phi negative. Okay, so in our paper, we also showed that we can construct this solution here. Okay, so here there are no bounds, no positivity. But we can still construct a solution, and it's a non-unitary solution. So there's one negative norm state with a negative OP coefficient. And if you keep flowing down, there will be more. So it's more like a proof of principle that this method can reconstruct these non-unitary solutions. And this is will be a theme later on, is that we can start off from positive unitary solutions, which maybe we can construct with the usual bootstrap. And then we can deform them continuously into a region of non-unitarity and maybe learn something.
Can I ask a question?
Yes.
Is there, so for these positive, for delta above the unitarity bound, we have these GFF solutions, generalized free field solutions, so that there always a solution. Is there something similar for non-unitary, below the unitarity bound, that there is a non-unitary theory that is always existent?
This is the non-unitary GFF.
Right. Okay.
If you just choose a GFF with delta phi negative and you do the conformal block decomposition, there will be minus signs.
Right, and it's known where the minus signs appear at the, yeah, okay, thanks.
I emphasize that the fact that these are free theories, it's really completely irrelevant from the point of view of this method, right? Because the GFF is as hard to bootstrap as some other more complicated solution. Because these equations, they don't know that this is a free solution.
But I guess you constructed also some, even in 1D, I think you constructed some less trivial examples which are interacting, right?
Indeed. So we use this method in later papers to discuss the flat space limit of ADS2 CFT1. Yeah. And in that case, we were constructing extremal solutions that were interacting. Indeed, they correspond to some interacting QFT in ADS2.
And but you did not try to continue those into the non-unitary region because that was not your focus.
No.
Okay.
So, okay, as I was saying, this is like this is the best case scenario. Everything works beautifully. But the minute that you want to go to something a bit less trivial, there are several difficulties that arise. And basically, these difficulties, they boil down to the fact that in the crossing equation, usually there are several channels which are labeled by some discrete variable. So discreteness is bad. We're talking about flowing in a continuous space, but once you have discrete variables, you cannot do this. So in the bootstrap, for instance, when you go to higher dimensions, you'll have spin. So there will be an infinite set of discrete channels that you have to worry about. But even, I think the simplest setup possible is in the BCFT, so boundary bootstrap. In this case, the crossing equation involves the bulk and boundary channel. So there's only 2 channels. So this is the next to easiest case. But even there are difficulties because Gliozzi's method also failed there. And so what happens is that the minute that you have more channels, usually what will happen is that these solutions with n over 2 operators often will not exist, at least with real scaling dimensions. And you can alleviate this problem by, adding more operators and giving some extra constraints. Or maybe you will alleviate the problem by asking that these equations, they are actually not solved exactly. They're only solved approximately. So these are the kind of things that Marco's talk discussed. But I think it's fair to say that usually this rapidly you run out of steam. And you cannot push this further. So it's a dream to push it to n equals 150 or whatever. So you need some alternative methods. So to get some idea of this alternative method, let us examine what happens in this nice case, in a very simple example where n is equal to 4. Okay, so I'm going to write these equations. There are 2 non-trivial operators, 2 auxiliary vectors. So there are 4 variables, the deltas, and the OP coefficients, and I have 4 crossing equations. And recall that there were these betas and alphas, which were the rows in the inverse matrix. So you can construct them explicitly in terms of some determinants, okay? So these are just some vectors. So for instance, one of the vectors, the the functional which is dual to d delta f1, so the functional which will compute mu1 is this object. Okay, so this is just one of the rows in the inverse matrix. It's clear, right? Because if you dot this vector into f delta 1, it will give 0. Into f delta 2, it will give 0. This guy will also give 0. It will only be non-zero if you dot it into this one. So it's indeed the row of an inverse matrix. And so our equations are that these betas, they should vanish, both of them. Okay? So to be very clear, even though I wrote this beta in terms of some determinant, recall that at the end of the day, this beta is just some combination of derivatives. So it's just a rearrangement of the derivative bases in a nicer way that will depend on these delta 1 and delta 2. So this is an equation that we can solve explicitly. But now let us examine this functional. So whenever you have a functional, you can dot it into the crossing equation to get the sum rule. Okay, recall that we started with the crossing equation, which had infinite constraints corresponding to the cross ratios, and then we truncated it. And the way that we truncated it is that we applied a finite set of functionals to it to get a finite set of constraints. Recall that these omegas are just whatever, some derivatives or something. So this is one basis. And now I'm telling you that it's more convenient to work with this linearly related change of bases in terms of these betas and alphas. But it's the same set of constraints. But now let us see what these constraints look like. Suppose that we can find the solution, one of these extremal solutions. What do these functionals look like? Well, let us take, for instance, beta 1. Beta 1 is epsilon f1, f2, df2. So what do we know? We know that it has to kill f1. It has to kill f2. And it has to actually have a double zero at delta 2 because of this condition. And so typically, if I plot the functional, it will look like this. Notice that it's 0 on the identity because this was my equation, right? This is the equation that fixes extremality, is that these mu's are 0. And this is nothing that the statement that when you contract beta with the identity, you get 0. So this is beta 1, and if you do beta 2, or in this case I chose beta 2 minus beta 1, it will look like this. So beta 2 minus beta 1, you see it has to have two first order zeros, one at delta 1 and another at delta 2. But so these sum rules have to hold. What does the sum rule mean? Well, suppose that we have positivity, that the OP coefficients are positive. Then you are integrating this beta 1 against the positive quantity, and you have to get 0.
Miguel, just to understand that I concrete, so beta 2 should have, I'm just repeating to make sure that answer. So beta 2 will have 0 at the origin, and then it will have a second order 0 at delta 1. Yeah.
Like this.
No, but at the origin it should vanish beta 2.
And at the origin, yes, indeed.
Okay.
Yeah. Beta 2
Okay.
look
Okay.
like this.
Yeah, it's just so that I make sure that I'm following you. Okay, thanks.
So I mean, again, this construction these functions just come out automatically once you have an extremal solution. But now, in the presence of positivity, they imply bounds. For instance, this functional tells you that if there were no operators below delta 1, it would be impossible to solve the equation, right? Because you want this sum to give 0, and you just get positive contributions. So this functional tells you actually that there has to be an operator in the CFT with dimension below delta 1. In other words, you get a bound on the leading scaling dimension. Okay? Which is exactly how we usually do in the bootstrap. In the bootstrap, usually we do the reverse. So we find the functional, and then if we want, we will construct this solution. So here I'm telling you to do the reverse. If you find a solution, then you can get bounds. But the important thing is really the solution. And the fact is that, for instance, this non-trivial bound would be missed. If you just compute this functional and you don't care about the solution, you would only learn about the fact that there has to be an operator in this region. But look, if you actually use the full solution, you can construct this other function, which also tells you something interesting. Now it tells you that not only there has to be an operator below delta 1, there has to be an operator between delta 1 and delta 2. Okay? Which is a non-trivial statement. And of course, there's actually n such bounds that you can construct by considering these betas and alphas. The alphas will give you bounds on OPE coefficients, and the betas will give you bounds on scaling dimensions. So there will be n distinct bounds that you can construct usually, all from one computation. So the message is that there's a very close link between these extremal solutions and the bootstrap bounds. So now we're going to turn the logic around again. We're going to use this link as guidance for correcting Gliozzi's method. And I put between quotes because even though Gliozzi had this key idea, I'm not sure that there is such a thing as Gliozzi's method. I mean, there's no such thing written down anywhere. There's some variations and people try different things. So I will propose some modification which in principle can work for any n. In particular, it will work in the unitary case for sure, because it will always reproduce the numerical bootstrap bound. So it's non-trivial because the usual Gliozzi's method will not do this. It will not reproduce it. For non-unitary, maybe it will, maybe it won't. I mean, I don't know. I will propose it, but I'm not 100% sure.
Hi, Miguel. How you numerically find the beta?
Find what?
Beta function. How you numerically compute it?
So suppose, how would you do this with SDPB, for instance? Run your optimization algorithm. Okay. You get the functional. Use the extremal functional method to extract the spectrum. Okay. And now you do this. You put all these vectors into some matrix. You put their derivatives. Actually, when you do the simplex method, you don't really need to do this because the derivatives, they automatically come out of the simplex method because you get these operators which are very close by. So you just put them all into a matrix and then we invert the matrix, and that's it.
Okay, thanks.
But so I don't understand. So you are saying that when we compute this extremal functionals using the SDPB, solving some extremization problem, actually, and then we say, okay, we solved the extremization problem, we have a bound. But actually, you are saying that if we were to do a little bit, just using the same SDPB output, we would do a bit bigger computation, just inverting some matrix, we would actually learn that the same computation computed a few more bounds.
Absolutely.
But sorry, isn't it just trivial? Because if you had an extremal functional from SDPB, if you go back to your slide, one slide, then you also find these bounds in the sense that there has to be an operator exactly at delta 1, exactly at delta 2, exactly.
No. Sorry. No. One thing is the statement that the solution which saturates the bound is unique. Mm-hmm. That's one statement.
Yes.
This is the statement that you're making, which is indeed trivial, is that if you have a solution whose gap is delta 1, everything will be fixed. I agree, but this is not what I'm saying, right? This is just a statement for general CFTs. In fact, usually what you find is that this functional looks like this. So actually you get a non-trivial region here. It's not even between 0 and delta 1. So already here you can learn something. You know that it has to be between delta 1 and this value. And then there are also these other statements. And these just hold for generic CFTs. I mean, it's not, it has nothing to do necessarily with the extremal solution. And for the alpha functionals, they're a bit different. So now they are negative on the identity, and then they are 1 at delta 1, and then they do this. And so now the contribution of the identity has to be canceled by these positive contributions. It will give you OPE bounds. And these are just general statements. They have, again, they apply for any CFT.
Okay, that's interesting.
Miguel, I still want to ask you something. So if I have n component in SDPB and I find n0 from the extreme functional spectrum, sorry, n over 2, 0, then I can do what you suggest. But if I find a less spectrum,
if you what, sorry?
If I find a less 0 from the extreme spectrum, what should I do?
If you find a what, a less, I don't understand.
Let's say my function will have n component.
Yes.
But I find 0 less than n over 2.
This is indeed what you will find generically. There will not be n zeros. If there were n zeros, the function will be 0. So you will have to.
No, but
So
Ning is
how
asking what if there are
this
less
better?
than n over 2 zeros?
Less than n over 2.
Yeah. That's what Ning asked.
This means that your solution is super extremal. It means that you don't even have enough degrees of freedom to solve the equation. So an extra parameter will get fixed, like delta phi would get fixed, for instance. We expect that this happens at the Ising kink, for instance. That this is one super extremal solution, that even the external parameters will get fixed. But
So-
usually you will find more than n over 2 operators.
So if it's less, can I still somehow construct those better?
If it's less, then you will choose some operators, and their OP coefficient will be 0. I mean, so at the kink, so when this happens, it happens at the kink, and at the kink there are several functionals, which are dual to the same solution.
Okay.
This
Thanks.
is the problem. The function is not uniquely defined at these points. Because of this problem that you can choose extra zeros wherever you want, because their OP coefficient will come out 0.
Thanks.
Okay, so let me review what we do in the positive bootstrap. So typically we have some problem, and again, this is not how it's formulated with FTPB, say, but let me emphasize that it's completely equivalent to this. So here I will formulate everything as a linear program. You can always formulate a semi-definite program in terms of a linear program. So you have these equations, and so typically we do something like, well, let us minimize over functionals inside some space, the functional and the identity, such that some positivity constraints are satisfied. So for instance, it's easy to see that if you solve this problem here, the function will give you a bound on the OP coefficient of this special guy, Q0. Okay, so this is what's known as a semi-infinite linear program. So it's very easy to see that if you have a function that satisfies these conditions, if you act with it on the crossing equation, you get that the OP coefficient is equal to lambda t minus positive stuff. So you get an upper bound lambda t, and then you minimize. So this problem is exactly the same as another dual problem, which is maximizing directly the OP coefficient, imposing crossing. And so the statement of duality in linear programming is that solving this problem or solving this problem are equivalent. Okay? And this will generically hold in the kind of problems that we are considering here, even with multiple correlators, whatever. This will happen. So then we can ask, okay, what are the special properties of the functional that solves this problem? So this has been formulated by these people, Karun Kushtucker, or Karush Kun. I think I made a mistake. Karush Kun Tucker, I apologize. They tell you that at optimality, when you solve this linear program for the functional, at optimality, then there will be a finite set of quantum numbers, Qi, and a finite number of positive lambda I squared, where I goes from 1 to k, and k will be smaller or equal than n minus 1, so the dimensionality of the space that you are working in, such that these equations hold. So the first equation is basically that these parameters, they solve crossing. The second equation is that the function has to have some zeros. And then this is really one of the key insights, is that the functional, not only, it does not just have simple zeros. The zeros, they have to be double, right? Because we want to ensure that the functional is positive. So if you're telling that it's 0 somewhere, it will have to be a double 0, except if your operator lives on the boundary of the space. Okay? I mean, so you are solving the problem in some space of quantum numbers. And so if your operator lives at the edge of the space, you're not going to impose positivity of the functional outside that space. So the function can switch sign there. So I think it's easy to see with an example. So I mean, recall that this is just, these are conditions obtained by solving the problem for the functional. So the first condition is very easy to understand. It tells you that at optimality, there is a solution to crossing. This makes perfect sense. I mean, the reason why this functional is optimal, it's because we cannot optimize further because there is a solution which acts as an obstruction to constructing a better functional. Since the functional has to be compatible with the solution, it has to have zeros. So this is the second equation. And the third equation, as I explained, is that these are necessary conditions for positivity of the functional. It has zeros. So in this case, my search space is all deltas larger than some gap. And so if one of these operators lives at delta 1, the functional is allowed to have a first order 0, but at delta 2, it will be a double 0. And so in the multiple correlator setup, how does this generalize? So besides delta, you will have these angles in OPE space, which tell you about the orientation of the operator with respect to the external states. And so as you vary this angle, the function will also have to have double zeros. So this is equivalent to positive semi-definiteness of the matrices.
But Miguel, but okay, now you are saying this looks like a trivial theorem.
Yeah.
We didn't know that such a theorem existed, but I think everyone will agree with this. But I thought that there was something less trivial before, that you were saying that there was n over 2.
Yeah, that this will come up. Yeah, I mean.
Okay, it's going to come up.
Yeah. Look, notice, I mean, k has to be smaller or equal than n minus 1. There's no n over 2 here.
Yeah, this n minus 1, why is it n minus 1, not n? What's going on?
Because if there were n constraints, the function would have to be identically 0 because it's an n-dimensional vector. So
okay,
it's n minus 1. So indeed, okay, let us see how we can solve these equations. So this will answer your questions. Suppose that k is equal to n over 2, which is the case that we considered already. Then the conditions 2 and 3 can be solved trivially. So basically the statement is that the functionals, they come for free. We can simply construct them as we've done before. So for instance, beta would be an epsilon tensor, and then f1, f2, df2, f3, df3, f4, df4. So this function would satisfy all these conditions, right? It will have zeros at the right places, and it will have double zeros at the right places as well. But if k is larger than n over 2, then this construction fails, right? Because I cannot fit all the vectors here. So let us see in a concrete example. Imagine that n is equal to 3, and you are trying to construct an extremal solution with 2 operators. There are 2 operators, then there are 4 degrees of freedom, and crossing only gives you 3 equations. Where does the extra equation come from? Well, let us construct the functional beta, which is just the external product of these 2 vectors. I mean, this is the same as this epsilon. So if we construct it like this, then it will be 0 on f1, it will be 0 on f2. So this is satisfied trivially. But now there's a new constraint that is not trivial, which is that this function should kill the derivative of this operator. So now this does not come out automatically. Okay?
What I don't understand, okay, so it's an equation for what? This one equation you say, it's an equation for what? For beta?
It's an equation for the data, for the dimensions that you put here. So in this example, the parameters are delta 1 and delta 2. You construct beta like this, delta 1 and delta 2. And now you impose that these equations hold, and this equation holds. And this gives you 4 equations for 4 parameters.
But what are we trying to do? Are we trying to show that sometimes this case k larger than or equal to is realized? Is this what we are doing here?
In generically, this is what happens.
Because this is what I don't understand. How do I, why is it not always that k is equal n over 2? I mean, they proved this theorem, but why?
I don't know. I don't know why. I mean, This is what's allowed, and this is what happens in practice. Generically, it will not be n over 2.
Can I also ask about this, like a sort of a follow-up? So this equation, the last equation, is some special linear dependence between some blocks and some derivative of some other block.
Yes.
So should we expect that when n is huge, like since derivatives of block, for instance, have very different behavior, close to say r equals 0, or z equals 0, z bar equals z equal 1, etc. So should we expect that these solutions which have more than n over 2 operator are more and more rare if n is very big? So if we probe more of
no. As you increase n, I don't have a ratio, but k is always larger than n over 2, and it's not just by 1 or 2. The number of such operators increases as you increase n.
Okay.
But can you give
In
us
the
some
beginning,
intuition?
for very small n, you might be lucky and there might be none, but then you start increasing n, and you start getting more and more and more.
Yeah, I'm lost, Miguel. I'm sorry. Because before you said that in the 1D case, this was not necessary. K was always n over 2. Did I understand it correctly?
But it's an experimental observation. I'm telling you that it happens to work. I don't know why.
Okay.
But it works. It didn't have to work. And the way I see it is that it must have something to do with the fact that now there will be spin. There will be extra discrete labels.
But and that's not clear from what you are saying that spin has anything to do with this. You're just saying there is some general theorem which says that k can be up to n minus 1.
Yeah.
And in some cases before, it was the case, it was always n over 2. And here somehow we empirically observe that the moment you introduce spin, you have to use the more general form of the theorem.
Yes. I don't have a good explanation why.
But yeah, but I'm sorry, I actually didn't understand very well this example. Like, can you go through it maybe? Because this is a crucial point. I always get lost at this point in your presentation. So can you just go through it once again? Like, what's happening here? You say equation. Can you explain what are we solving for? What are the unknowns? What are we trying to find? Because it's not clear.
Sure. So this is the crossing equation.
Yeah.
And we've set n equals to 3. So there are 3 equations here. We are trying to find the solution to this equation using 2 vectors. If we had 3 vectors, it would be trivial.
So 3 equations for what unknowns? Which are the unknowns?
The unknowns are the values of the scaling dimensions and the OBE coefficients.
Okay.
And you are searching in this space to see if it's possible to come up with a solution to these equations. Okay?
Okay.
So there are 4 parameters and there are 3 equations, so the system is underdetermined. So usually if you just take this equation, you put it into Mathematica, you will find that there's an infinite set of solutions. And then you don't know what to do. You have to choose one according to some criteria. But now here we want to say, well, I want not only a solution to crossing, I also want that there will be some functional bases associated with this solution. Okay?
Mm-hmm.
And furthermore, this functional basis, it has to have double zeros at the position of these operators. Mm-hmm. This is required in the positive bootstrap problem. So this is what we are doing now. Okay, so let us try to construct such a functional. So the functional, you saw that it has to satisfy these conditions, and it has to satisfy these conditions. So let us try to construct it. Well, let me define this functional to be f delta 1, f delta 2, outer product. Then these 2 conditions will be automatic. But this condition will not. And so this gives me a 4th equation that will constrain delta 1 and delta 2. So overall, I'll have 3 plus 1 equations for 4 degrees of freedom. And then in principle, I should be able to find a unique solution. So usually Gliozzi's method just includes this. And so the system then is underdetermined.
We have how many equations do we have? 4 equations.
Yeah, overall I have 4.
Yeah.
I'm saying that this is the new ingredient. It will be a non-trivial constraint on these parameters, delta 1 and delta 2.
And in this particular case, you knew that since n was odd, you knew that k could not be equal n over 2. You knew that they had to choose this larger k.
Yeah, okay, it turned out like that. Yeah.
But suppose that n is equal to 4. Then we have to do a choice. We can try to find a solution with k equal n over 2.
Yeah.
And then if it doesn't work, then we have to switch to k.
Absolutely. Absolutely.
Okay.
Absolutely. We don't know what k will be a priori. We don't know. So
But
you
have
have
to
to
still
try.
I mean, still find that number of tries.
You have to try. Yes. So it's annoying. This is indeed one of the issues that I will discuss.
Okay. Thanks.
So as I said, when you solve, so if you just do the numerical bootstrap and you find the solution which saturates a bound, experimentally you will find that k is larger than n over 2. It's just a fact of life. And so what this means is that so I call these tangency conditions, these conditions on the function. They are really crucial to determine the solution and how to flow the solution uniquely. And so this number k minus n over 2 is some kind of measure of how sparse the solution is. And so, for instance, something interesting that is allowed by this is that there can be singularities, for instance, the kinks, which will correspond to jumps in this discrete number. So sometimes the number of operators will change. And this will correspond to some non-analyticity, like a kink. Okay? And so what is the proposal then? I'll propose that even though these things, they were motivated by unitarity and positivity and bounds, I propose that even for the non-unitary case, we should demand these tangency conditions. Okay? And if you want a motivation that has nothing to do with unitarity and positivity, is that if you want to be able to deform a solution uniquely, you need these conditions. So you want your functionals to form a basis. If you don't impose the conditions, you will not get a full basis of functionals. Okay, so now how can we solve these equations? So, well, in general, this is hard. So I mean, I'm not saying that I've found the solution to all our problems.
So Miguel, sorry. So now we are still in the what are we discussing? Are we still discussing how to find these functions or how to deform?
Well, now I'm going to tell you how to solve these equations ab initio. I mean,
so that's
if you have a solution, if you have one solution, then it's very easy to deform because you just linearize these equations and you use Newton's methods. The problem is getting one solution.
Okay, that's the main problem. Mm-hmm.
Because, yeah, so these are some complicated nonlinear equations in these quantum numbers, and you see that in the semi-definite case, there will be many continuous variables, but even worse than the continuous variables are the discrete ones, because you have to make choices, discrete choices. So, you know, in general, this is just hard. You have to make these discrete choices, and you also need to specify k, as Slava was mentioning. And so you have to do some multi-dimensional search in this space. So in general, this is just a hard problem to solve. So I can offer maybe two possibilities.
Sorry, can I ask a question? Do you have a non-unitary case where you've chosen these additional conditions on the derivatives, and it flows to sensible theories?
Yes.
Is there a reason why?
Yeah, I will show. I will show an example. Otherwise, this talk would be.
Yeah. No. Okay.
I'll give one example.
Okay.
So the first statement is that regarding guessing, this problem is present even in the k equals n over 2 case. And I suspect, and we had a bit of a discussion about this already, is that in this guessing problem, it's very likely that we need to use good functional bases. So even in this k equals n over 2 case, so this plot is basically essentially equivalent to what I showed you before. If you use the derivative basis, this is what the operators do as you increase n. So the dashed lines are the correct solution that they will eventually asymptote to. And you see that as you increase n, the operators in the extremal solution, they start being more and more wrong relative to the correct solution. But if you use a different basis, so these alpha n's and beta n's, there are some special functionals that you can construct exactly analytically. If you use this basis to solve the same problem, then you see that the behavior is much nicer. So basically what this means is that it would be easier to guess the solution, to come up with a good guess, and then use Newton's method. So again, this is in this very simple k equals n over 2 case, but I suspect that the same thing will be true now in higher dimensions, that we should use good bases of functionals which capture the right asymptotics of the solution. And there are indeed some proposals in the literature for such bases. But in general, it's still a very difficult problem. So let me propose something a bit different. We will use the fact that the numerical bootstrap automatically constructs a unitary solutions to these equations. Okay, when you solve this linear program, the output is exactly a solution to these equations. So we'll do this in a unitary region where we can use this method. And then we'll deform continuously. So this is easy to do because we can just use Newton's method to deform and eventually reach other interesting solutions, for instance, which will be non-unitary. So I already showed an example of this in this trivial d equals 1 case. I am proposing to do the same thing now in higher dimension. Let me just mention also that, of course, these flows are also useful in the usual unitary bootstrap, because doing this flow, it's orders of magnitude faster than just rerunning the optimization algorithm. So yeah, I think this should be implemented for multiple correlators. Maybe I'll mention this at the end. So let me show you what the typical workflow would look like. So we're in d equals 2. In d equals 2, the bound, or in d equals 3, the bound looks a bit like this. There is a kink. The kink is at the Ising point. So you construct an approximate pair of functional and spectrum using SDPB or whatever. So in this problem, usually what you find is that you do a binary search. Here there's a functional, here there's a solution, and you zoom in on the allowed region. So we learned in this conference that there's a more efficient way to find this boundary using this navigator method. So there's also something that will come out recently in the work with my students, something called correlator minimization, which also allows you to zoom in directly on the boundary. But anyway, so suppose that you have a decent enough pair functional solution at that point. So once you have a good enough guess, you can take these equations, plug in the guess, and use Newton's method to correct it so that you really reach the exact boundary. When I say exact, it's like as close as you want. So if you know this spacing to whatever, 10 to the minus 3, it's very easy to use this method to obtain 10 to the minus 30 or something. It's very fast because you don't need to do optimization. So now we have a good initial point where we have an extremal spectrum and the basis of functionals that goes along with it.
Miguel,
So
what
now
do you
we
mean?
can deform
What do you mean by the spacing 10 to the minus 3? Do you mean like that every operator has stabilized within 10 to the minus 3 accuracy?
No, 10 to the minus 3 in this spacing.
But
The
then I'm surprised.
higher operators, they will be more separated.
But I'm surprised that the Newton method could work. Is it going to work on this setup? Because
Depends
suppose that
on
the high operators are completely wrong.
It depends on n. It depends on n.
Okay.
So for higher n, you can use your navigator or this other method. You have to get closer. You have to get maybe 10 to the minus 6 or something such that the high dimension operators are sufficiently close such that Newton's method will work. But this can be done.
Okay.
And then when you use this Newton's method, these high dimension operators, they will be perfect. I mean, the spectra that you get in this way, they are just perfectly clean. I will show a spectrum later on. So now that we have one solution, we can deform it. So we can get all these solutions. And at every step, we have an extremal solution and the basis of functionals. So in particular, we learned that there are bounds on delta epsilon along the flow. Does that make sense? So the bounds are just like a consequence of this construction. Okay, now, as you do this flow, there can be some singularities. So there can be these operator swappings that I mentioned. or some OP coefficients, they can go to 0 or whatever. So whenever this happens, you are faced with a choice. Because these equations that I told you, they don't really care about positivity of the OP coefficients. If you enforce it, then you will stay in the unitary branch, and you will follow the bound that you get from the bootstrap. But you might choose to ignore it. You might say, well, this OP coefficient has become negative, so what? Let me continue flowing and see where it leads me. Okay? So very concretely, in D equals 2, I think probably this was mentioned in Connor's talk yesterday. We know that the bound looks like this. And there's a line which is saturated by some minimal model correlators. And this line actually, so this is the 2D Ising point, but the line continues. And in particular, it crosses at minus 2/5 the Young-Lee model. So the question is, can we flow along this line to reach this point? And so let me show you some results. So these are very preliminary, but so these are done with n equals 6. So it's still very small. But even though it's n equals 6, these extra conditions are required. So k is larger than n over 2 in this case. And so this is the unitary branch. So all these solutions, basically, they were constructed using this method, starting from some initial one here, and then I flowed to get these ones. And then these curves, the purple ones and the red ones, they correspond to flowing along a non-unitary branch. And the reason why there are 3 is that actually, in this region, there are several singularities that occur. So the kink is actually characterized by many singularities that occur in a very short region. And every time that there's one of these singularities, you can choose to go along one branch or the other. So this is a problem, by the way. Right? Nevertheless, in this case, you are lucky. I don't know. I tried 3 different of these singularities and flowing. So these are all extremal solutions. And then when you flow, so they don't really follow this minimal model line, at least with this n. But maybe by chance, they all converge here at the Young-Lee point. Well, very, very close. So the Young-Lee point is here at minus 0.4. And these solutions, they cross here at minus 0.39.
Have you tried following the unitary branch past 0?
Well, this is what I've done.
No, like if from...
Here?
Yeah, exactly.
No, this I've not tried.
Okay.
So let me just exemplify what's going on. So these are the spectra that you get using this method. So as you can see, they are very clean. So the red lines are the spin 0 spectra. Blue line is the stress tensor. Then there's some spin 4, spin 6, spin 8, spin 10. And so basically, this is the Ising kink. And you see that there are several singularities. I'm not even showing all of them. But for instance, the spin 6 operator is not always present. That sometimes it appears, sometimes it disappears. Same thing for spin 8. So there's some swapping of spins. You have spin 4, spin 6, spin 8, spin 10. So my cutoff in spin in this case was spin 10. And there's this scalar operator that shoots up, and actually it goes to infinity, and then it comes back down in the spin 10 channel. So you can really, the advantage of this thing is that you can really track this very carefully, and the spectra, they are really very clean. And so I think to these unitary branches, I flowed maybe, I forget, but, well, I think there was one I flowed here when this guy disappears. Maybe when this guy disappears, and then some other point here where this scalar operator has disappeared. So these are the 3 branches that I followed, and then they all converge to the right place. And again, these extra tangency conditions are required. You would not find these solutions with Gliozzi's method.
If you only followed one branch, you said there was a singularity of an OPE coefficient going to 0 at the kink, which gave you a choice. But once you flow to the Young-Lee point, is there something else which tells you that you've reached a special theory?
I didn't investigate. I mean, at various points along the flow, other OP coefficients, they become negative. So you could think that those are special points as well. So, but basically, after making this initial choice, then I don't care what happens. I just keep flowing no matter what. This might not be the correct thing to do, by the way.
Yeah, because in higher dimensions, here it's nice because you can see that the line passes through the Lee-Young point. But that's sort of cheating. We already know where it is because it's...
Well, Young-Lee is characterized by the fact that there's an exchanged operator whose dimension is the same as the external dimension. So you could use that as your criterion in higher D.
Yeah.
Okay.
Yeah, can I ask a question about this? So, okay, so there are two things which can happen. If we coefficient becomes 0, I understand that this can be dealt with easily, even though this may happen several times. Is there some, is it harder to deal with the case than, for example, two operators collide?
I've never seen two operators colliding.
Oh, that's nice.
So what I do see is that the functional can develop a new 0.
Okay.
So the functional is positive and then starts coming down, and then when it touches the axis, then you have to do something as well if you want to preserve unitarity. So I mean, it's messy and there's a lot of coding involved, which partially explains why I haven't really developed this much. No. But okay, so let me just conclude. I've already gone way over time. So what's the outlook? So I think that independently of this non-unitary story, it would be good if someone with enough energy really implements these flows for the multiple correlator setup. I mean, it sounds like in this navigator story, you're already doing something similar, right? Because you are also linearizing around the extremality and then doing this quasi-Newton method. Maybe it's even the same thing, I'm not sure. It's just that here, I don't really run optimization again, whereas you guys, you are guessing and then optimizing. So I don't know. In any case, I think there's some room for doing something in that case. And then, as I said, so there are two possibilities for constructing these non-unitary solutions, and they both have problems, and quite a few problems. So in the direct construction, there are all these ambiguities. You have to choose the discrete labels. You have to choose K. Then you have to perform this multidimensional search. I mean, it's a hard problem. I would start by examining the boundary CFT case because there's only 2 channels. And in some cases, we know what the exact solutions are. So maybe this is a good starting point. Again, using better functional basis could help in this case. And then in the flows, here we are kind of lucky that things worked so well in this example that I showed you, because there are also many ambiguities, because you have this kink, there are many transitions that are happening. Which one should you choose? Sometimes you might choose one and then it will flow nowhere. There are also ambiguities in that case, and it's not clear how to choose the correct branch. In this case, in the end, it didn't matter much. All 3 branches ended up more or less at the same point. But in general, I expect that you will have to make some choices. And finally, so as I said, to improve this, you can either construct better functional bases, but another line of approach might be to, instead of increasing n, you could increase in the number of crossing equations. So going to more and more correlators. Maybe this problem will be less sensitive to the UV, and so maybe it will be easier to come up with these guesses. I don't know. So there's a lot of work to do and things to try. So I will stop there. So questions? Yeah, we have a question here from the audience.
Yeah, you said that it didn't really matter which branch you chose because they all end up at the same point. Isn't this just something that distinguishes this point? And does this happen for any other points?
Yeah, so
if you would choose a few other branches, is there another point that you would get this?
I don't know. I haven't tried. I made these plots last night, so
okay.
I tried these 3 and they gave this.
Could it be a way to single out interesting theories?
So I expect that you could choose some. In fact, maybe I even tried. Yeah, I think I tried one where when I started flowing, then the flow stopped.
Oh.
I could not keep going.
Yeah.
I think this is one of the, when the functional develops a new 0, I tried that one. I just said, so what? The functional has a new 0, let me keep it going. So the function will become more and more negative. But if I try to do that, then the flow, things went crazy. I forget, maybe some operator went to infinity.
Right.
So I could not flow.
But perhaps if you choose some other branches, then it does work and it crosses at another point.
Maybe, as you said, I'm not even showing all the singularities here. There are many of them, and you can really determine precisely where they occur. So it's a question of trial and error. It's just annoying because you see there are 10 spins. There are many things that can happen. I think it would be better to try to play with the BCFT setup. Because there, we also know that there's a unitary case that might be interesting, so we can compare.
Okay.
So here you're flowing from a unitary solution and continuing to non-unitary. In the multiple correlator setup, where maybe you have some small height corresponding to unitary, would you still expect the flow to be useful, or would it just kind of turn around?
So we said so there's an island. So there are two things that we can do. Wow, this is a really neat island.
I think you need
so it's something like this.
You need to switch to a pen instead of ships.
Okay, sorry. So okay, you have the bound, and then whatever. There's some island here. So you always need a solution. So you need to solve some optimization problem inside this island. So one of the optimization problems that you can solve is maximizing, going towards the boundary. So if you go towards the boundary, then you can go around the island, and you could map its shape very accurately. Or if you are inside the island, then you could say, well, let me minimize the central charge, for instance. If you do that, then you will again get a pair. You'll get an extremal solution. And then you can smoothly deform it anywhere that you want inside here. So, it depends. Like, if you have 1 million core hours at your disposal, you can just do many runs on your cluster and you're happy. But if you have a laptop, maybe you just want to do this once and then get all these other points essentially for free. So, or you can do a mixture of these two approaches.
I think, Miguel, I just wanted to comment that this looks pretty amazing. Congratulations.
Thanks.
It's, I understand it's very, very preliminary, and as you say, you did this plot last night, but first of all, it's a fantastic illustration of your method, which I think was lacking desperately because we heard this many times, but somehow nobody got around to try to do something like, nobody had any good idea what to try it with, and I think you had an amazing insight to try to get this Li Yang point, and I didn't know that it was lying on that, and it works just I think beyond any expectation. It's really, it really opens up a new direction in this whole business.
So I think now one really needs to increase N max and see if this story still holds, if we can still do these flows and so on. It's possible that you might have that you will run into singularities along the flow that even in the non-unitary case you might have to fix. So, but yeah, I think it's one should try to explore this.
But remember how it worked for 3D, right? We said, okay, in 2D it works, it should work in 3D as well. So now you say, okay, for 2D Li Yang it seems to work, so there are reasons to be hopeful.
I remember this famous talk that you gave, I think it was at Jussieu, where you made this plot with the 2D, and I was a bit inspired by that, but let's hope that we eventually end up with the same conclusion as in your case.
Yeah, I think we should be hopeful. Well, so there is I don't know if you see as a chair that there is a raised hand of Ning.
No, but just speak up if you like.
I have a question. So, imagine you do this with mixed correlator.
Yes.
Imagine you do it with ON. So in that case, I imagine, let's say you start with n equals to 2, and you gradually decrease n.
Yes, I think
let's say
the applications, right? And this n is n in O(n).
Yes.
And D is space-time dimension.
Yes.
But it doesn't have to be in the multiple correlator setup, right? Even in the single correlator, I think it's interesting.
But let's assume we do mixed correlator, and we try to find the island, and on the island we try to go to the minimal navigate point. So we have a unique spectrum, and we gradually decrease n.
Yes.
Then at some point, I can imagine the island will get smaller and smaller and disappear. At that point, my navigator value is 0. So at that point, I guess I can read off the spectrum and look at which operator decouples.
So you don't. It doesn't have to be at that point. I don't understand. If I understood this navigator story correctly, you are just choosing a clever optimization problem that will work even in the infeasible region, right?
Yes.
So actually, you can. Once you have this good objective function that you chose, then you can flow even outside the feasible region. So this method that I'm describing, these extremal flows, they will also work in that case.
Yeah. But what I want to say is that I think in that case, there will be very different branches if you use your language. Because I imagine one branch would corresponding to go from single correlator bound, approach the kink from the right, and then pass through the kink and approach to the left. That would be one branch. But I imagine that branch probably is not the correct branch to get, for example, n-2.
It's not the what, sorry?
So one branch is the branch like you did here.
Are you saying that there's a branch that goes like this and there's this one that goes like this?
No, I'm saying there will be another branch which will be an extra axis in n. So that would correspond to extend the kink to n-2.
Yes.
So in these two branches, it must be in one branch there one set of spectrums decouple, and you have to allow those set of spectrum have negative OP square. But in another branch, there are another set of spectrum whose OP square become negative. Then I feel it might be difficult to go to the correct theory. Do you have any remark?
Yeah. I think if I get the gist of what you're saying, yeah, in general, there will be several possibilities on how to go into these non-unitary branches. And you'll have to make choices. And in general, you just have to explore them and see if you get something reasonable. So I think this is what you're saying. I wanted to comment that first, in the case of O(n), you could hope that as you lower n, sometimes you lose the kink and it becomes something which is a bit more round. And you say, oh, the theory has disappeared. But it's possible that there are still some transitions going on. And so, so you have some rounded kink. And now basically you could, if there's still some singularity here and one here, then you could flow this way. And you can flow this way, and then you would see where they intersect. And this would define a kink for a non-unitary, in the non-unitary case, when n is whatever, 1.5 or 0.3 or something. Maybe this could be a way of arriving at some special corner.
Okay.
So in this case, in your language, you see the island would have disappeared.
Yeah.
The island would have disappeared here.
Yeah. So around the kink, there are actually many singularities. Some corresponding to decouple of a very high operator. Some have more clear physical meaning.
Yes.
I would imagine those low delta operator have clear meaning, but for higher delta, it could be just a numerical artifact.
Yeah, so we know that, for instance, in d equals 2, at least in D equals 2, all these singularities, they seem to get squeezed together at a single point. In D equals 3, it was not so clear whether this was the case. I think probably people expect that this will be true as well, but I don't think this has been examined in detail. But so then it would be irrelevant. But,
so you already did some experimenting in D equals 3?
Well, we did it in our paper, right? We saw that there were all. We saw that in D equals 2, the kink was a lot sharper than in.
In that sense, yeah.
Yes, but I've run this code in D equals 3 as well. Yes.
Thanks. Miguel, I just want to say, I think what you said can be very effectively implemented in navigator approach.
Yeah. So for instance, in this language, I think when I'm flowing along the zero of the navigator function, right? When you're here, you're flowing along the zero of the navigator function. Maybe you've already implemented all this code. I don't know. In your talk, from what I understood, you start off with a point and then you jump to another point. When you jump, you hot start the SDPB with this new function, with your guess for the functional. But if you do a very small jump, is it possible that you don't even need to run SDPB again?
I guess you can extrapolate the checkpoint to effectively start SDPB. But actually, in the navigator approach, what you will see is that those singularity you talked about corresponding to the discontinuity in the second derivative of the navigator. If you go along the bound precisely, you will see the second derivative is not continuous. And that precisely corresponds to some kind of operator decouple.
Yeah, but I think this is a bit of a red herring. I mean, this will be true for any observable. In fact, I didn't show this, but I have it in the mathematical code. So if you plot the derivative of this curve, which you can do very accurately because there's like 500 points here, you'll see that the derivative, it's non-analytic, has jumps and whatever. So the second derivative.
The derivative is analytic, but the derivative of the derivative is discontinuous.
Why? It's not analytic. It does not have a finite derivative itself. It's a continuous function, but it's not analytic. And yes, so the second derivative will have jumps.
Which function?
I'm saying that usually we just plot this delta epsilon. If you plot its derivative, then it's very clear that there are many kinks.
That don't disappear if you just increase.
Well, they shrink, they get closer and closer together as increase. And sometimes there are special points that you might just miss altogether if you focus just on kinks. There can be non-analyticities that do not give kinks in these plots, so it's really essential to examine the spectrum.
Don't give visible kinks.
Sorry?
They don't give visible kinks, but under the microscope.
Under the yeah, maybe.
But I didn't understand, Ning, when you said that this could be implemented with navigator functions. So some of the things that Miguel mentioned could be implemented, but for example, flowing into the non-unitary region, I mean, this could be implemented, but it's going to be hard to implement because that part of Miguel's proposal would be hard to implement with navigator, not immediately.
What I had in mind is this. Actually, I had a discussion with Marco after his talk, but it's after you left. Basically, what I had in mind is that let's imagine you do this O1 island image correlator, and you go to the minimum navigator point, and you gradually decrease n. And as you decrease n, you also keep track of the spectrum. So at some point, you will see the navigator go to 0, so the island disappear. But then, as you go to that point, if you look at the spectrum, you will see those operator decouple. The OP square go to 0. Once you find such operator, then you immediately allowed this operator to have negative OP square and sum it up with the vacuum block and stun this operator.
But what are you going to assume about the OP coefficient of that operator?
You have to scan it.
No,
but Miguel didn't have to scan it. You know, he had just to solve the equations, and it was more immediate.
This will work exactly at the point where the island disappears. But then, if you want to keep going, the dimensions will move.
Yeah, the dimension will move. So, in my proposal, you will have to stun this operator, stun its dimension with its OP coefficient.
But the crossing equation will not suffice to fix them. So you will have to impose these tangency conditions. I think I understand what you're saying, but it will be equivalent to what I'm proposing. It's not just sufficient to scan. The crossing will not suffice. You will have to impose that the functional that comes out of SDPB will continue to exist even in this non-unitary region. Otherwise, these operators, they will move and you won't know how to fix them.
Okay, I see.
Why are you saying that you don't know how to fix them? Isn't that due to the fact that you only used up to n equations?
No.
Once you're in the non-unitary regime, right? And we would just fix the coefficient.
No. Once you're in the non-unitary regime.
Yes.
Well, how do you know? How do you get the solution? I don't understand.
We flip the sign and we're demanding positivity on the opposite. The opposite polynomial. We flip the sign of the polynomial that we're demanding negativity.
Sure. Yes, I see. Yes,
no. What I said is slightly different. What I propose is that I let this OP coefficient to be negative, and I sum it up with the vacuum block. That will modify the vacuum block.
But then it will move. What do you mean you added up with the vacuum block? In order to get some optimization problem which will recover the solution, you'll have to put some ranges where you flip the signs of OP coefficients. But at some point, the operators will move and they will cross these ranges. And then what do you do?
I think that the approach would be that this operator would be, and I think you watched at the zero of the navigator function, exactly which operator you have to flip. And as long as it doesn't move exactly through another operator on which you're demanding positivity, then there is no problem. So the idea would be this operator would probably
also have to impose some gaps, right? Because if you allow things to connect with where you flip the sign of the OP coefficient.
Right. So in practice, you would also, for the other ones that you're demanding positivity that are close to these ones, I guess that you would.
You don't need to put in a gap. You can sum this operator with the vacuum and
no,
for
but
the
guys,
rest you still demand
Ning and Barton, what you're proposing is not going to work for the Liang, because for the Liang, there are going to be many operators with negative OP coefficients. It's not just going to be 1 or 2 or 3. They're going to be, the number of operators with negative OP coefficients are going to be comparable to the number of operators with positive OP coefficients. So what you're proposing, it might work right next to the region where you exit the unitarity region, where there's just 1 or 2 operators with negative OP coefficients. But the moment you flow to Liang, there are tons of such operators. You have to have a systematic procedure which does not allow you to treat these operators separately, like from positive operators. And I don't see how what you're proposing is going to get you there. I mean, it seems like, I mean, it's a very natural idea what you're suggesting, but the reason why nobody has tried it before is because it's just not plausible that it's going to work for Liang. Well, what Miguel is proposing seems to be plausible.
I agree that it's not clear that it's plausible, but I think one reason why people haven't tried is that also it used to be expensive. So okay, what was the procedure that we proposed? Exactly as Ning did. You see one operator, you change its sign, it changes. Now you can with this change sign, you can again go to the minimums, find the next operator that changes the sign, and you can iteratively try to do this. And of course, this might be prohibitively expensive. But one thing
let me just say that
sorry, what can
if you manage to get it to work, the outcome will be the same as what I'm proposing.
And I'm not saying that this is better or any. So I think this is a beautiful method, and I just wanted to explain that one reason that it hasn't been tried is perhaps also that it was clear. Well, it used to be even more prohibitively expensive, because if you had to scan over all these operators, then it was clear that it was hopeless without the navigator. So at least we got closer into reach of this being possible. I'm not saying that it is good, and probably Miguel's solution is much better. But
I think it will be this. I think that what you're saying is for the time that it will work, it will match what I'm saying. It's the same, because you'll get a solution and a functional. So you are solving the same equations. But okay, if there's a very urgent question, otherwise I suggest that we at least close the recording and.
So before
Go down from.
Sorry, before closing the recording, maybe I would like to, maybe in the name of every organizer, I would like to thank, so this is the end of this program. I would like to thank the people that for all this month has assured a good participation and a good activity for this program. I would like to thank the people who came here, to the young postdocs and PhD that took the risk in these times to participate on live. And I would like to thank the speakers, because they all played the game of doing introductory course, but the community in this program, the different communities in this program can enjoy. Personally, you know, this program has had 3 main communities: statistical physics, NED CFT, and the 2-dimensional CFT. And I, for example, that comes from 2D CFT, I really enjoyed. I feel like I know a little bit what is going on the, for example, on the NED bootstrap program. And then finally, I would like to thank the Institute of Pascal to make this possible. And I will tell you, for the people who does not know about this, yeah, this is the resumation, but let me say that the Institute Pascal has a wonder. We have witnessed that I can say that it is a wonderful place to stay, and there is a wonderful staff behind that allow this program to be possible. And I hope maybe that this program will become periodic. One never knows. But if you one day you want to organize a program, please think to the Institut Pascal in Paris-Saclay. It is a nice place. So I think I finished my. So basically, yeah, the resume is thanks to everyone. And now we are. I cannot say that here, but thanks to everybody. And if the other organizer wants to say something, it's the time.
I want to say, I want to thank all the organizers who were actually physically present there, because I was never present. So I was joined it from the distance, and I think thanks to you guys.
You have been the most present of us all.
Well, virtually present, but if it were not for you guys, Sylvain, Raul, Kai, Miguel, who were there and who were it was important. It was very important that there were some people, I think, physically present, and there were some organizers physically present. And on the other hand, I also got feedback from many people who could only virtually be present, and they still they were very happy that they managed to participate. And I think this format revealed ultimately quite successful. So yeah. Thanks, everyone.
No. You can end up at the last recording.